All right, here's some titration curve problems. This says select from A, B, C, and D the curve produced by the addition of ammonia to 25 milliliters of hydrochloric acid. So you need to know that ammonia is NH3, and that's a weak base. Okay, the only strong ones, remember, are the ones that make a B on the periodic table. And then hydrochloric acid, of course, that's a strong acid. Okay, so we're adding ammonia to the hydrochloric acid. So the hydrochloric acid is in the beaker right now, and it's got a pH probe in it. And so we're going to start at a really low pH, and then as we add the weak base to it, it's going to get a little bit bigger and a little bit bigger as we go along, until eventually we get to a semi-high pH. But remember, it's a weak base, so it's not going to get very high. And so our titration curve should start like way down here, like around 1 or 2, and then it should go up, and then we'll have a steep part, and then it should level off here, not super high. So 14 should be way up here, maybe it'd be around here like 10 or so. And so the one that I find that's kind of like that is letter B right here. So this one should be letter B. The second one said ethanoic acid to sodium hydroxide. So this one now has sodium hydroxide in a beaker, and NaOH, as you probably know, is one that makes the B on the periodic table. So that's going to be a strong base. And so that means when I start inside my beaker right here with my pH probe, I'm going to have a pretty high pH. So I'm going to have to pick one where it starts really high, like 13, like this. And then when I add to it, I'm adding ethanoic acid that you might or might not know what it is. It doesn't make any difference as long as you recognize it's not a strong acid, because it's not hyperhydroxyl high homohydroxyl OH2SO4. So this is a weak acid. Ethanoic acid is also known as acetic acid, in case you wanted to know that. So I'm going to go from a really high pH, and I'll go down, down, down. Then I'll have a steep drop, and then I'm going to level off. And I'm not going to get super low. I'm not going to get down here to 1. But I will get down, below 7 or so. And the one that I find like that is this. You can see it gets down to maybe 4.5 pH or so, which is letter C. Okay, then the last one, sodium hydroxide to 25 milliliters of hydrochloric acid. So once again, I'm starting at a really low pH for hydrochloric acid, just like this guy right here. And I'm going to end at a really high pH because I have sodium hydroxide. So I'm starting really low, ending really high, so that should be letter A. All right, then let's look at these. The answers below are correct except 13B should have a flat part of the curve circled, not curve B. Okay, we'll watch that in just a second. It says, which titration curve represents the addition of a strong base to a strong acid? So, you can't really tell the exact numbers of the pH here, but you want to pick the one that starts at the lowest pH for a strong acid. And so we start really low right here compared to here and compared to here and here. And then we're going to add a strong base, and so we end up really high right here, so that's why it's letter B. Then it says circle the portion of a titration curve where buffering is occurring. So you can only have one that has lots of buffering when you have a weak acid or a weak base. And so if you look at this titration curve, you can see it doesn't start quite as low as this one, and then it still ends up here really high, but this would be the area of most buffering right here, where you'd have the weak acid and its conjugate base present. And if you want to see more calculations on that, look back at another video where I do a little bit more with buffers in there, because this is the area of most buffering, and we've got a weak acid and its conjugate base present. And then which pH titrant curve represents the titration of a weak base by addition of a strong acid? So here we have a weak base right here. It starts fairly high, and then we have a strong acid and it goes down really low, so that would be letter C. And then the last page, I'm just going to switch the pages out here really quick. have another titration curve here. And this one says which type of titration does this curve most likely present? And so you can see it starts really low, like around 1, and it ends pretty high, like above 12. So this is just like one you did in the lab, and so this would be a strong acid, strong base titration. If it was a strong acid, weak base, you'd end up like right in here. If it was a weak acid, strong base, you'd start here and you'd end up going way up here. If it was weak acid, weak base, you'd get the one that I drew on here that was, weak and not, starting pretty high and ending like kind of medium-ish high. Circle the equivalence point and label it. So here's the equivalence point. This is where there are the moles of acid equal to the moles of the base, and it's the middle of the steepest part of the curve. Number 100, if the titrant is 0.01 molar NaOH, calculate the moles of NaOH added at the equivalence point. So for this one, I need the molarity triangle. And so I'm given the molarity right here, and I know at the equivalence point I have 40 milliliters right here. So 0.01 molar times the liters, which is 0.04. That's 40 in liters. And then that ends up being 4 times 10 to the negative 4th moles added. And then the moles of acid in the sample. Well, I know at the equivalence point the moles of base are equal to the moles of acid, and I've neutralized them, or I've found the equivalence point. And so this is also the number of moles of acid in the sample. Then number 101 still uses this titration curve, but it actually puts some substances to it and asks a question and says it's 0.2 molar HCl is in a beaker with a pH probe. So that's starting right here. And then it says the titration curve above is collected at the titrant, and the titrant is 0.5 molar rubidium hydroxide added. Calculate the milliliters of HCl originally in the beaker. So we know that when we reach the equivalence point, the moles of acid are equal to the moles of base. And if I substitute in for moles, molarity times liters, I would have the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. And so if I know that the rubidium hydroxide moles are 0.05 molar, and I know its volume to getting to be equal to moles of acid is 40 milliliters right here, I could multiply those two together to get what this is equal to. I know the molarity of the acid is 0.2. So let's write those out. And I will write MAVA is equal to MBVB, and the molarity of the acid is 0.2 molar. The volume of the acid is unknown. The molarity of the base is 0.5 molar, and the volume of the base is 40 milliliters, so 0.040 liters. Divide both sides by 0.2, and I end up with my volume being 0.1, I believe, liters, which is 100 milliliters. And we would want to go to 2 sig figs, so it would probably be 1.0 times 10 to the second milliliters for the volume of acid originally.